We start now section 3.2 on page 113. It's about measures of spread, or we can say measures of dispersion or measures of variability. So, and these measures are just for us to learn how far the data values are from the center or how concentrated the values are around the center. So this is what we want to know now. So the last time we learned about the center of the data set. Now we're going to learn about the level of variability of the data set. So the first one is going to be the range. The range is defined on page 114. And the definition is very simple. The range is just the largest value minus the smallest value, or in other words, the range is the maximum value minus the minimum value. So in R, we can just enter our data set as usual. So X equals lowercase c, then parentheses, then we enumerate all the values in our data set. Then we close the parentheses, and we can use two functions to find the maximum value or the minimum value. If you have a lot of values, hundreds of values, these functions are very helpful, maximum and minimum of X. Otherwise, if you have few data values, then you can just find the maximum and the minimum just by inspecting the data set. So we're going to solve a problem to find the range. So this example is on page 114, is example 3.11, and the example is the following. So they say, we have here 3.11. So the problem is the following. We're going to compute the range of temperature data, of the temperature data for San Francisco and St. Louis, and interpret the results. So what they are talking about is about this table 3.3, that shows the temperatures in San Francisco and St. Louis. So you have here those temperatures from January through December. So we're going to enter those values into R to find the maximum and the minimum, just for you to see the functions. But you can inspect the data set and find right away what the maximum and the minimum values are. So let's see. So in our problem then, we are asked to find the range. So using let's see, temperatures in San Francisco and in St. Louis. So this is the problem. So we're going to compute the range. So we're going to find the range of the temperatures in San Francisco and St. Louis. So you can see from the table that the maximum value is for San Francisco. So we can find the maximum and the minimum just by checking the list. So you can see here for San Francisco, the maximum value is 63, the minimum value is 51. So 63, 51. So that means that the range is just 63 minus 51, and this is going to be just, if you use your calculator, this is just 12. So 12 is the range of the temperatures of San Francisco. Then we have St. Louis. So let's check the list again. So let's find the maximum value. You can see here 79 is the maximum value and the minimum value is 30. So 79 is the maximum and the minimum is 30. So now we can compute the range for the temperatures of St. Louis as 79 minus 30, and just this is going to be just 49. So 49. So that's what we do to find the range. This is just a measure of spread, or measure of dispersion, or measure of variability. Let me show you just how to use R to find the maximum and the minimum, and also the range. So let's use R now. So we have to enter first the temperatures for San Francisco. So let's do that. So we have the temperatures for San Francisco. Then we're going to do the same thing with the temperatures for St. Louis. So let's type this in. So I have temperatures for San Francisco. Let's check if we did the right thing. So San Francisco, the maximum value is 63, as we found before. The minimum value for San Francisco is 51. And the range, you can just find the range just for you to see how R computes those values. So it's giving you just the minimum and the maximum, so you need to do the difference to compute the difference by yourself. So for San Luis, then instead of typing maximum and minimum, you can just type range of St. Louis. That's what you're gonna get is just the minimum value 30 and the maximum value 79. So R doesn't compute the difference. You need to do it by yourself. But it's giving you the minimum and the maximum value. So now we're gonna move on and work on a different measure of spread. So that this the range is not as is not commonly used. There are better measures of spread, or measures of variability. The second one, and maybe the most important one, is the variance. The variance is described on page 114. So in that page, we have formulas. So you can see here at the bottom of that page, you can see the definition for the population variance. So we're going to have a formula for the population variance, and we're gonna have a formula for the sample variance, and they're gonna be slightly different. So let's work on this then. So let's write this down on our notes. So we're gonna have a formula for the population variance. Population variance is gonna be denoted by using the Greek letter sigma, and we're gonna write sigma square. So this is the lowercase s in the Greek alphabet. So sigma square is going to be just the sum of the differences between any value and the mean of the population, and those differences are squared before getting the sum. Then we're going to divide that by the size of the population. Remember, we use capital N for the size of the population, and also we have a formula for the sample variance. So the formula is slightly different than this one. First, we're going to use lowercase s square, for the variance of the sample, and it's going to be also the difference between every value and the corresponding mean of the sample. Now we're going to use x bar for the mean, and also the differences are squared before getting the sum, and we're going to divide that by the sample size, but -1. So that's the slightly that's the difference between these two. So remember, when you are computing any value from the population, this is going to be a parameter, and if you are computing any value, numerical value from the sample, that is going to be a statistic. So those are the differences. So this is the most important part. I'm going to write just here before doing the examples. The other measure of spread, which is the standard deviation. The standard deviation. The standard deviation is just by definition the square root of the variance. So it is the square root of the variance. So that's the reason I wanted to show you that. So for example, the standard deviation of the population is going to be just sigma, and it's going to be the square root of x minus mu square over n. Or if you already have the variance, you just take the square root of the variance. The sample standard deviation is going to be just s, and it's going to be the square root of the sum of the differences again between any value and the mean of the sample, and those differences are squared, then added, and finally the sum divided by n minus 1, and we're going to take the square root of that, and that is going to be the standard deviation of the sample. So there is something very important that I need to tell you. Language R only computes variances and standard deviations of samples. So this is important. So anytime that you use a command like to get the variance or to get the standard deviation in R, you're getting the standard deviation as if the data set was considered a sample. So if you are working on a population, you need to do an adjustment. You need to multiply by n and divide by n minus 1 or vice versa, depending on what you are looking for. So let's work some examples, and then we're going to be able to finish this section, which is simple. You're going to have some problems to solve. So let's continue with the example 3.12 on page 115. So it's going to be about computing. So we're going to compute the population variance, for the San Francisco temperatures, Okay, so that's the information that is on table. So this is on table 3.3. Table 3.3 on page 113. So table 3.3 on page 113. So we already have the information in R. So we have our values. So we're going to use a formula then in R. So you enter X, the temperature, so whatever value that you're looking for, then you're gonna get the sum of the differences. So we're gonna compute the differences. So we're gonna use a double parenthesis because we're gonna subtract x minus the mean of x, and we're gonna square this. So and we're gonna close this. So this is the sum of the differences square, and we're gonna divide this in this case by capital N. So the number of data values that are in the list. So we need to check how many values do we have. This is 1 year of monthly value, so there are 12 values. So N equals 12. So let's use R to finish this problem. So we already have X, which is San Francisco. Let's do that now. So in our case, what we're gonna do is we're gonna get the sum, and remember double parentheses. I'm just putting an extra space for you to see that first we compute the differences. So what are the differences? Any value of the temperature in San Francisco minus the mean of those values. So, and then we're gonna square this. So, and then we're gonna add everything. So we sum all those differences and we divide by 12, which is the capital N. So we're gonna get 14.083. So that is gonna be sigma square. It's gonna be 14.0833. So that's the variance of the temperatures. So let's continue with our work. So you just wrote here the variance. So and you can do these computations also by hand. If you want to do the computations by hand, if you have a calculator available, a very simple calculator, this is what you need to do to solve this problem. So we have the temperatures for San Francisco. So we have the temperature. Let's say this is going to be my X. So we have the first value is 51, then 54, and the last value is 52. So there are 12 values of temperature values. So the first thing is that you're going to add up these values. That is going to be the sum of X, and you're going to divide that by 12. So in that way, you're going to get the mean. Since you are working with the population, then we don't use this notation. We use this notation because this is a population of temperature. So it's going to be the sum of X over capital N. So if you do these computations, you're going to find 57.5. So that's the mean. So now the next column is going to be just the differences between every value and the mean. I can enclose this into parentheses. So you're going to have the first one is going to be 51 minus 57.5. Once you get the difference, you can use your calculator and square that value immediately. So you're going to get, in this case, negative 6.5. That if you square it, you're going to get 42.25. Then you do the same thing with the next value. Now it's 54 minus the mean of the population, 57.5, and then we're going to square the difference. The difference is negative 3.5. We square this value and we get 12.25. And you continue. The last one is going to be just 52 minus 57.5. The difference is minus 5.5. We're going to square that and we're going to get 30.25. So then we're going to add these values here. So the sum, so this sum you can write is the sum of this column, x minus mu square is going to be 169. That is going to be the sum. Then we can compute the variance. The variance is going to be just this value, 169 over capital N, which is 12. And you're going to get the same value that we got by using R, 14.0.83. So this is if you want to do the problem by hand. But yeah, it's better if you just enter the information in R and try to type this formula carefully. Be careful about these parentheses. So everything is important, every detail when you are using this, because if you just start receiving error messages from R, that means that you maybe mistype something. So you need to check your typing again. Okay. So that's the variance. So let's see what is the next problem that we're gonna work on. So we have the standard deviation. So for this problem, so we have the sample variance. So we're gonna work one more example. So now it's gonna be, we're gonna compute the sample variance. So we computed the population variance. Now we're gonna compute the sample variance. So the formula is the same as the one that I gave you before. So, but now it's indicated that this is a sample. So let's work example 3.13. So example 3.13, it says the following. So it says that a company that manufactures batteries is testing a new type of battery designed for laptop computers. They measure the lifetimes in hours of 6 batteries, and the results are 3, 4, 6, 5, 4, and 2. Find the sample variance of the lifetime. So what we need for this problem is that we are working with battery lifetime. So this problem is on page 116. And we have the following information. We have the values of x. The sample is just 3, 4, 6, 5, 4, and 2. So there are 6 values. So n now is lowercase n because this is a sample. This is a sample. So n equals 6 values. So what we're gonna do is we're gonna apply now the formula that says that we're gonna get the sum again, but now it's gonna be the difference between x and the mean of x, and we're gonna square those differences, and we're gonna get the sum, and we're gonna divide by n minus 1 because now it's a sample. We're computing the variance of a sample. So let's do that. So we're gonna go and use our console. So we have now x is going to be equal to the lifetimes of those batteries: 3, 4, 6, 5, 4, and 2. So those are the lifetime. So we're gonna get the sum. Again, we're gonna get the difference between every value and the mean of the sample, and we're gonna square that, and we're gonna complete the sum, and we're gonna divide that by n minus 1. N is 6 values minus 1. So if we do that, we're going to find that the standard deviation is just 2. The standard deviation of, sorry, the variance s squared is going to be equal to the variance. We're still working with on variances. So let's write this down. So now using the symbol s squared for the variance of that sample. So this is the sample variance. And again, if you want to do this problem by hand, you need to have your table, you have x, you write vertically the 6 values, then you get the sum of these values, so the sum of x, and you're going to divide that by n, so to get the mean, so the mean is going to be the sum of x divided by n is just 6. So if you do these operations, if you add up these values and divide by 6, you're going to get 4. So now your next column is going to be x minus x bar, and the other column is going to be just the square of this difference. So now we are using x bar because now we are dealing with a sample. So in the first case, you're going to have 3 minus 4. Then you have, this is going to be negative 1. If you square this, you're going to get 1. Then in the next case, you have 4 minus 4 is going to be just 0. If you square 0, you get 0. Then you have 6 minus 4. This is 2. If you square that, you get 4. Then you have 5 minus 4. This is just 1. If you square it, it's just 1. Then again, 4 minus 4. You get again 0. And finally, 2 minus 4 is going to be negative 2. If you square it, you get 4. Then you're going to get this sum. This sum is going to be the sum of this column. This column is x minus x bar square. So you get the sum, and the sum is going to be just 10. Okay, 4, 8, 9, and 10. Then the variance of the sample is just this value 10 divided now by n minus 1. So n is 6. So n is 6. 6 minus 1 is going to be 5. So 10 over 5 is going to be 2, which is the value that we got by using R. So that's the variance of this sample. So now I think it's now your turn to work on problems like this. Let me see. And remember, if you need to compute the standard deviation, you only take the square root of those variances. So take the square root. How do you take the square root? By using R. Let's see, I'm going to show you. That's the last thing before giving you the assignment. So to take the square root, you just need to, for example, in this case, you're going to write Sqrt, that's the square root of 2. 2 was the variance for this sample. So 1.41 is going to be the standard deviation for this sample. And we can check that. You can use SD to get the standard deviation of the sample. We cannot use SD for a population. That's the reason I gave you the full formula. But remember, if you're going to take the square root of the variance, you just use Sqrt parentheses and then the thing that you're going to take the square root of. So let me just give you your assignment, the first part of your assignment for this lecture. So you're going to solve 3 problems from the corresponding exercise set. So this is section 3.2 exercise set on page 126. These exercises, you're gonna compute the variance and the standard deviation. So you just finish your computation of the variance and take the square root, and then you get immediately the standard deviation. You're gonna work 3 problems: problem 20, problem 22, and problem 24. So let me show you the problems, and then you're gonna have a break for you to solve those problems. So this is on page 126. So I have here page 126. So 20, 22, and 24. So you have here those problems. So first 20 is just this data set, starting at 59 and ending at 17. So you have this data set. Then 22, another, and read carefully. In 20, they say find the sample variance. So they are giving you a clue on the formula that you need to use. In this case, they say sample. In 22, they say population variance. So that's important to use the right formula. And finally, 24 is again, you're gonna find the population variance and standard deviation for the following population. You can use R, or you can use just work on your tables and use your own calculator and do it by hand. It's up to you. But yeah, try to use R to become more familiar with the R console. So in the last part of this section, we're gonna now work with frequency distributions, like this one. Remember. So and now we're gonna compute the variance and the standard deviation with group data. So again, the formula that we're gonna use when you work with a frequency distribution is gonna be different than the one that you use when you are working with a data set. So a data set is just what we just worked on a moment ago. Now we're gonna work on a frequency distribution. So we're gonna use the formulas that we used the last time to compute the mean, and now we have two more formulas to compute the variance of the frequency distribution. So remember, we have a frequency distribution. Usually it's going to be something like our classes, then we need frequencies, and then we're going to find midpoints, and once you have that information, then we're going to be able to use our formula. So this is a frequency distribution, or group data, as they mentioned in page 119. So this is a frequency distribution. So you have classes, you have frequencies, you have midpoints, and when you have just a list of values, so that's a data set. A data set is when you only have your values of X given by a list of values. That's a data set. And the formula that you use to compute the mean and the standard deviation are different. So in this case, if you remember, the mean is just the sum of X over N if you are working with a sample, or over capital N if you are working with a capital N if you are working with a population. And the variance, again, you just learned this in the previous part of the video. It's just the sum of the differences with respect to the mean square, and you divide by capital N. Or if you are working with a sample, then the variance is again the sum of the difference with respect to the mean square, divided by N minus 1. Now, if you have a frequency distribution, so a table where you have frequencies and classes, and you compute midpoints, remember you're going to need to compute midpoints, then these are the formulas that we're going to use. So first, we're going to need to compute the mean of the frequency distribution. It's just the sum of the frequencies, the sum of the products of the frequencies and the midpoints divided by the sum of the frequencies. So this is something that we covered in the last lecture, the last part. And then we have two formulas depending on whether you are working with the frequency distribution that corresponds to a population or a frequency distribution that corresponds to a sample. So the difference is going to be again the denominator. So instead of having just the sum of the frequencies, now you have the sum of the frequencies minus 1 if you are working with a sample. If you are working with a population, it's just the sum of the frequencies in the denominator. The numerator is kind of similar to the one that you just worked. So you're going to need to compute the differences again between midpoints and the mean. You're going to square it, but you're going to multiply that also by the frequency of every value of every midpoint. So you're going to need to use R because doing this by hand is going to very time consuming. So I'm going to write for you the formulas using R. So let me see, and then we're going to work a problem, and that is going to be the end of this lecture. So this is then for a frequency distribution. So you're going to have a frequency distribution. So the first thing is that we need to compute the mean. So, and to compute the mean, we need the frequencies. So you're going to enter the frequencies by using again the lowercase notation. And then you enter the midpoints. You previously computed the midpoints in the usual way. And then you're going to compute the mean. And we're going to give this name to the mean, capital mean. It's going to be the sum. And you're going to multiply frequencies and midpoints. So we did this the last time. And we're going to divide that by the sum of the frequencies. So, and then we have the mean. Then you just compute the sum and you're gonna multiply the frequency and the differences and the difference between the midpoint and the mean, and you're gonna square this, and then you're gonna divide that by, in one case it's just the sum of the frequency. So this is when you are dealing with a population. If you are dealing with a sample, then essentially we're going to write the same thing, the sum, again the frequencies multiplying the difference between the midpoint and the mean. We're going to square that and we're going to divide that. We need an extra parenthesis because we're going to subtract 1 from the sum of the frequencies, and that is going to be the variance. Then you take the square root, so you're going to take the square root to get the corresponding standard deviation. Why? Because these formulas are to compute variances. So these are to compute variances, the variance of each in each case. So let's work on an example to understand this better. So we're gonna work on example 3.17. Example 3.17 is on page 120, and they say that we're going to compute the approximate sample standard deviation, sample standard deviation of the number of messages sent using the data given in table, the data given in table 3.6. So and that table is on the previous page, page 119. So you have here the data. So it's just a frequency distribution. So you have your classes in the first column, and you have the frequency. So you're going to need to compute then the midpoints. So what are the midpoints? You remember, I think we already solved this problem the last time. It's just 0 plus 50 divided by 2 is going to be 25. Then you just add 50 to every previous value of midpoint. So you're going to have 25 plus 50, you're going to get 75. So essentially you are getting the midpoint between these two, then 125, then 175, then 225. Those are going to be the midpoints. So let's write that down. So you're going to have something like the following. So we need the class is just 049, 1599, 100, 149, then 150, 199, 200, 249, and finally 250, 299. Then we have the frequencies were given 10, 5, 13, 11, 7, 4. Then we were talking about the midpoints. The midpoints were 25, 75, 125, 175, 225, and finally 275. And with this information, we're gonna be able to use R. So you don't need to do the extra work. So you just need to enter frequencies 10, 5, 13, 11, 7, 4. Then you enter mid points is just 25, 75, 125, 175, 225, and 275. So let's enter this information into R, and be careful with R commands. You need to use lowercase letters for your R commands. So let's see. So I'm entering now the information, and I'm getting an error message. Yeah, why? Let's check. So my frequencies are here, my midpoints are here, my first formula for the mean is here, and then I got an error message here because I'm using capital letters for sum. Remember, I mentioned before that we need to use lowercase letters for the R commands, and I'm using capital letters for my variables, the ones I am defining. So I'm correcting that, and now I'm getting the right variance. So this is a sample. So this is S squared equals 5975.51. Then I'm going to take the square root of this value to get the standard deviation. And with that, I'm going to end this problem. So the standard deviation S is just 77.3142. So this is the problem. So let me check the book, and then we're going to continue with the final assignment corresponding to this class work. Okay, so let's check the book. So the book uh, get, yeah, you have here the standard deviation is 77.3014. We got 77.3142. So we got the right standard deviation. So I think now is your turn. You're gonna work now on these exercises that I'm going to assign, and that is gonna be all for today. So you're gonna work. I'm going to write here. It's just 2 exercises. So we are on section 3.2, exercise set, and this is gonna be on page 126, and you're gonna work problems 26 and 28. So those are the problems that you're gonna work. So let me show you the problems for you to take a picture, and then that is gonna be all for today. So now you're given a lot of frequency distributions here, so you can play with as many as possible. So okay, 26, you're gonna approximate the sample variance and the standard deviation given the following frequency distribution. You only have 5 classes. So with frequencies 2, 14, 6, 13, and 15. And then you're gonna work on problem 28. You have 6 classes in this case. And again, frequencies 18, 11, 6, 6, 10, and 5. So solve these problems and send your results through Canvas in the usual way. So, and that is going to be all for this lecture on measures of a spread, or also known as measure of dispersion or measures of variability of the data.